Now for this section, we're going to look at diffusion. Now, diffusion basically just involves the random walks or random motion of molecules, and it leads to, basically things dissolving or spreading out in one another. And the reason why this takes place is because when things are mixed together, they're actually more likely to occur than if they were separate. Now, in order to do this in a reasonable frame, we do have to set some limitations on our system. So the limitations that we're going to set on all our diffusive systems are the Brownian limitations. And the Brownian limitations are probably new to most of you. They're very similar to an ideal gas with one key exception. So to start there, if you've ever worked with an ideal gas molecules basically are free to move around however they like, and they're also free to pass through one another. Right? So when you're looking at, the ideal gas law or whatever, that assumes that gas molecules can actually just phase right through each other, which is not really a proper physical model, but it is the easiest to deal with. The Brownian system is one step up from that. Our molecules are still free to move around. They don't really interact at a distance with each other, but they can actually pass through each other. So if they hit one another, they bounce off. And that is basically the Brownian assumption. Now, when dealing with the Brownian assumption and we look at diffusion, there's basically two different areas that we can look at. The first area we can look at is if we have a certain concentration of them located in a well-defined area, how many of them are going to be able to cross a particular boundary. And we quantify this by using a quantity known as the particle flux. Now, the particle flux J here is a unique quantity. What it basically tells you is the rate of change at which molecules are passing through this barrier per unit area. That's why there's a 1 divided by an area here. And this dN by dt is just simply how many particles per second are passing through this boundary. If you like, you can also replace this with delta n by delta t. Now, one of the characteristics of Brownian motion is this particle flux, this number of particles per unit time passing through an area, is actually related to the difference in concentration between the inside and the outside of the box. That's the delta C that's present here. It depends on a diffusion coefficient, which depends on which molecules you have moving, their sizes, and what environment they're located in, as well as delta X here. And delta X is basically how far they have to go, right? Or the size of the barrier that they have to cross. Now, delta C by delta X, you've probably heard of it here before. It's actually known as a concentration gradient. So if you've ever sat through chemistry or biology and somebody is telling you, I have a concentration gradient, what they're saying is they're comparing a thickness or a distance between two different systems and looking at how different the concentration is between these systems. So they're taking this difference in concentration and dividing it by how far these systems are apart. And basically you can use this to figure out for most simple systems, including biological systems, such as, potassium ions crossing a cell bilayer, exactly how much is flowing in or out. Now, this diffusion coefficient here can be calculated theoretically, but 9 times out of 10, it's measured experimentally. It's far faster to simply measure these things experimentally. And lastly, this is of course limited to a one-dimensional system. For the purposes of this class, we will not be talking about diffusion in more than one dimension. Now, we can have a diffusion of particles. Very, very similar to this is a diffusion of heat. When dealing with diffusions of heat, we can use a thermal energy flux, H here, as opposed to our particle flux, J. And what this basically describes is it, again, is per unit area, but it describes the change in thermal energy. That's what this capital Q is, per change in time. And instead of depending on a diffusion coefficient, it depends on a thermal coefficient. And instead of depending on a concentration gradient, it depends on a temperature gradient. So these two equations here are almost exactly the same, and they're treated exactly the same. The only difference is we give the constants different names, and we're relating flow of heat to temperature gradient in the thermal one, and flow of particles versus concentration gradient in the particle-based one. But in terms of dealing with them, they're literally identical. And that's no surprise. If we do have particles moving around, typically speaking, empty space doesn't carry heat very well. There's usually something in there that carries it. And so what we end up with is, if particles are diffusing, they're probably also the medium in which heat is carried through. So it's not super surprising that these two equations aren't quite different. However, the most useful one is actually the Einsteinian diffusion coefficient, which is the next thing, or the diffusion relationship, which is the next thing we're going to talk about. Now, this diffusion relationship answered a very, very useful and simple question. Say you have some distribution of solute or items or liquids, and you put them into a larger system, which I'm going to put in blue here. Now, as per diffusion, this drop of whatever or bunch of objects you put in the center is eventually going to spread out over time. And so what you might want to figure out is how quickly is it going to spread? Now, doing some mathematics, this is one of the things that Albert Einstein is relatively famous for. He actually figured out a nice simple relationship where you can figure out how far this spread is going to go over a particular amount of time. Or you can figure out, where is this thing spreading out going to end up at some later time. And his relationship you'll see down here at the bottom in the purple box. Now, when interpreting it, there's a bunch of things for you to realize. First of all, the t here is just the change in time. It's how long this diffusion has been allowed to sit. D here is the exact same diffusion coefficient that was present in the particle diffusion case. But we're going to talk about the other two variables here, d with the little bar on top of it and n. N here is the number of dimensions that you're allowed to spread in. So I'm going to write this down, is the number of dimensions you can spread in. And this is relatively important because diffusion actually works differently if you're diffusing along a surface versus if you're allowed to diffuse throughout a volume. In other words, if you have a system in which all your particles have to float on the surface of it, they can only spread in 2 dimensions. So n would be equal to 2 here. If you take your particles and you confine them to a very, very thin cuvette or pipette, and they can only spin or spread forwards and backwards, n will be 1 in this relationship. And if you take these your solute particles and dump them in a center of a bucket, and they're allowed to spread in all 3 dimensions, n will be equal to 3 here. So this diffusion fundamentally changes depending on how your system is allowed to spread. And that is actually a relatively common theme for the area of science that deals with items on the nanoscale. Because the idea is when you're dealing with things that are constrained, they can behave very differently than things that aren't. So n here is the number of dimensions. So if you're spreading along the surface of something, n is going to be equal to 2. That's a relatively common one. And if you're allowed to spread throughout the volume, n will be equal to 3. Now, the very last thing is d bar here. D bar is how far from wherever you dropped your thing do you expect to be at on average. So this is statistical quantity. Yes, you could have little juts or little tiny areas of uneven spread, but what it basically finds for you is what is the average, radius of spread do you expect to have, right? Or how far from where you place this original concentration of particles are you likely to be able to reach? And the reason it uses d here is because it's an effective displacement of particles. You put them in the center, and now they have the ability to be displaced up to this outer edge.